Hello and welcome to another lecture of classical motion of a single particle. So, in this lecture I will do a little bit of digression from what we were just discussing till now. So, as you can remember that for a simple harmonic oscillator we discussed the solution in the presence of a forcing, in the presence of the viscous drag, and also we started with the very simple one where there was neither any force nor any viscous drag. And in the next week's lecture we will also discuss about the combined effect of both this forcing and dissipation. But at this point the students can have the impression that the way we approached the inverse square law of force was quite different from that what I am now doing with this simple harmonic oscillation. Here we are just reducing everything in 1D and we are saying that something very without losing any generality, something very easy to solve the equation of a simple harmonic oscillator in 1D, and finally that according to the equations since every directions are decoupled from each other. So, if you and they are similar from to each other, that is why if you somehow find the solution in one direction or in one dimension, then that will be similar for the other dimensions. But now the question comes that can we do the similar type of analysis of motion directly from the central force of motion's point of view. So, that means that we started this harmonic potential as an example of Bertrand's special force law. So, Bertrand's theorem said that when f r is proportional to 1 by r square and f r is proportional to r, in both cases for every bounded motion we will have a closed trajectory. So, bounded motion will have a closed trajectory always. Okay. Now, from that we discussed this inverse square law and then we introduced this law, but we then never discussed in detail the similar type of analysis of this bounded motion, unbounded motion, effective potential energy, all those concepts which we introduced for a central force law, and finally also the orbits. Okay. So, in today's lecture what I will do before going to this before analyzing the motion of a simple harmonic oscillator in 1D in the presence of both forcing and dissipation, here what we will first do, again we will go back to our original discussion of central force and we will see the simple harmonic oscillator more like an example of a harmonic potential which is a subcase of a central force. So, just for this case f r is equal to minus k r, where k is greater than 0, and then so this is the force law, and then the potential or the true potential will be simply given by minus integration f r dr, which will be half k r square plus c. Here you see that what we will do, we define the potential at r is equal to 0 to be 0, and that actually helps us to get rid of the c, because c then gets to be 0. Remember, this is different from an inverse square force law where we say that potential is 0 when r is infinity. Okay. So, this we define, and finally once again this does not actually make any problem, because in physics we are always interested in the dynamics where the gradient of potential comes into play. So, whether you are just defining some reference potential at reference potential to be 0 at r is equal to 0 or r is equal to infinity, finally does not matter. The only thing we have to understand that we always have to account for potentials to be finite, otherwise you can have a problem to find the force. Okay. So, we define the potential at r is equal to 0 to be 0 and c is equal to 0, and simply that gives us V r will be half k r square. Now, the two things, the equation of dynamics will be m r double dot minus r theta dot square is equal to minus k r, and the energy conservation will be given by E is equal to half m r dot square plus L square by 2 m r square. This is quite general for all central forces, plus the true potential, which is different for different potentials. Okay. So, here for our case it will be half m r dot square plus L square by 2 m r square plus half k r square. Now, you see what is the stark difference between this potential, this total energy expression, and that for the case of an inverse square law. So, if you remember that in inverse square law the true potential energy was negative, okay, and that is why there is always a possibility of having the total energy to be positive, to be 0, to be negative according as the true potential energy and the true kinetic energy competes with each other, and sometimes when the true potential energy wins, we say that the total energy becomes negative, and when the true kinetic energy wins, we say that the total energy is positive. When they are balancing each other, we say this is the case of zero total mechanical energy. Now, here there is no way that the total energy can be negative, because this is positive, and this is also positive from our definition, because k is also greater than 0 from this definition. Okay. So, the first conclusion is that we cannot have any case of negative energy. Okay. We can have some 0 energy. Well, this is also a little bit difficult to understand at this point, and as we will see that this is also not possible, okay, from our analysis which we will do in a minute. Okay. Now, once again just to tell you that this part, I take red, this part is the effective potential part and this part is the effective kinetic energy part. So, I just write this thing is equal to half m r dot square plus L square by 2 m r square plus half k r square. My first question is, can we draw a diagram of V effective as a function of R? So, this is simply V effective. Okay. So, you see that here this is quite easy. When R tends to 0, okay, then this term getting very small, okay, but this term is getting large enough, so that your V effective will be approximately L square by 2 m r square, and that is why you will have something like this. Okay. Again, when R tends to infinity, then this term goes off very quickly, but this term dominates, then V effective will be half k r square, and that looks like something like this. Like this, okay, and so yeah, like this, and so when we are just combining these two, the potential, the resulting potential should be given by this. Okay. Yeah, and we just erase this part. Now, you see what is the very speciality in this case. In this case, you see first of all the potential energy is actually always positive. Now, always the question is that whether it can touch 0 or not, we will also see that. Now, the potential energy has a minimum possible, okay, and the effective potential energy of course has a possible minimum, okay, and above that always it is having a well type structure. So, if you just see that the system has an energy which is just equal to here or here or here or here, always the particle will have two turning points. So, one R min and one R max, both of them are being finite if your energy is finite, okay, and then you will always have bounded motion, always have bounded motion. Okay. Now, what happens in this point? Okay, many questions can be answered if we know this. So, for that we know this is V effective will be, so the V effective will have some minimum value. So, DDR of V effective will be equal to 0, and if you do this DDR L square by 2 m r square plus half k r square is equal to 0, and from that you can actually take minus L square by m r cube plus k r is equal to 0, and you have r square r to the 4 is equal to L square by m k, and r will be simply L square by m k whole to the 1 by 4. Okay. I call this as R 0. Okay. Now, remember what is the meaning of R 0? So, that is R 0. So, R 0 is the radius of the circle, okay, which is the trajectory of a particle which is moving under this effective potential, because when if the particle is having an energy which is exactly equal to this point, then the particle has only one possible r, but it does not say that the particle is at rest. It can always have some other theta values, and that is only possible when you have a purely circular trajectory with this radius. Now, what will be the value of V effective then? So, after that I can also calculate V effective minimum will be equal to, and actually you can just do the another step just by saying that this, if you do, let us say this type of, so d2 V effective dr2, you can actually have this is equal to this thing, this, okay. So, this is again minus 3, so it will be 3 L square by m r to the 4, okay, plus k. Now, you see that this is always positive. You do not have to even check the value of r at this point, because r to the 4 is always positive, this is always positive, and that is why, if I have not made any mistake, minus 3 L square, yes, that is true, yeah, that is why V effective will only have a minimum here at this point of R 0. Okay. So, what will be the minimum value of V effective at this point? That will be L square by 2 m R 0 square plus half k R 0 square. If you now take this is equal to L square by 2 m R 0 square, and instead of half k R 0 square, so you can actually write, or R 0 4, R 0 to the power 4. So, R 0 square will simply be L by root m k. I can write r to the r04 by r0 square. This is just a trick to write in a convenient way. You can write whatever you want. Okay. Then I write half k. So, r0 to the 4 actually I wrote L square by mk, L square by mk r0 square, because r0 square is here. Okay. Then this k will go away and finally you will have L square by 2m r0 square plus L square by 2m r0 square, and you will have L square by m r0 square. This is positive and greater than 0, and that is why this point should always be here. So, you see that the minimum of V effective is actually above the x axis, okay, above V effective is equal to 0. So, it will be something positive. So, I can write this is the value where V effective is equal to L square by m r0 square. This is simply a square, yes. Okay. I can write this also. So, this expression I can also write as L square by m. Now, 1 by r0 square I can write as root mk by L, and I can have L root over k by m. Now, remember, just because we have also discussed the exact solutions of simple harmonic oscillation, k by m, root over k by m is nothing but the omega, right, the natural frequency. So, V effective is exactly equal to L times the natural frequency of the oscillator. Okay. This is very important result for a simple harmonic oscillator. Okay. In 2 dimension. Of course, now you know that whether, since this is a central force, we can always take the force effectively, I mean the motion effectively in a plane. Okay. So, the last point here you see, then you can have, after seeing this whole picture, that okay, if I now have an energy like here or here, then I will actually have an unbounded motion. What is this? So, if I give the system more energy, the system has a bounded motion, and I am giving the system less energy, then this is performing unbounded motion. Then this is actually of no use, okay, because you see that you cannot give the system an energy which is less than the V effective minimum, because if you give the system a total energy which is less than the V effective minimum, that means you are actually giving the system a negative kinetic energy, which has no meaning in classical mechanics. So, the minimum possible energy of the system, the total minimum possible energy will be exactly given by the V effective minimum, and you see at that point, okay, the particle will actually perform a purely circular orbit. Okay. We have already analyzed the motion of a particle under a harmonic potential, and we have seen that if you give a realistic possible total energy which must be greater than the V effective, okay, minimum effective potential energy, then we have seen that the particle will always go through a bounded motion with some finite r minimum and r maximum. Okay. So, now the question is, since it is the special force law under Bertrand's theorem, this force proportional to r, and hence the quadratic potential law, the question is that I mean, of course, we know that in such situation a closed trajectory is guaranteed for every bounded motion. So, now the next question is, what is the nature of that closed trajectory? Can we find an equation for that orbit? Okay. And that is why we will now write the next topic, that is the orbit under a harmonic potential. So, here again the routine process is to go through Binet equation, which is nothing but d2u d theta 2 plus u is equal to minus the force law by m h square u square. and f of 1 over u is equal to simply minus k by u, because this is equal to minus k r. So, this is exactly equal to minus k by u, and then you can write d 2 u d theta 2 plus u is equal to k by m h square u cube. I call this thing, since this is a constant, I call this alpha. So, this will be alpha by u cube, okay, where alpha is nothing but k by m h square. Now, the question is how to solve this for u as a function of theta to find the orbit. So, this equation is not a very straightforward equation to solve, but we will see that although a little bit tedious, finally we can find analytically the trajectory just by using this method. Okay. So, what I will do? I will use some mathematical trick to multiply this equation by 2 du d theta. If I do this, 2 du d theta times d 2 u d theta 2 plus 2 u times du d theta is equal to 2 alpha by u cube du d theta. And here you can easily then say this is nothing but d d theta of du d theta whole square plus d d theta u square is equal to, how to write this thing as d d theta of something, you can also do that. This is minus d d theta of alpha by u square, okay, because if you calculate this term, this will be minus 2 by u cube du d theta, and alpha will be there. So, minus go away, and finally, you will have 2 alpha by u cube du d theta, which is nothing but this. Okay. Now, I can simply say I can just take d d theta of, and I will have du d theta whole square plus u square is equal to minus alpha by u square plus some constant. Okay. Now, if you just remember the conservation of energy for an arbitrary central force, you will actually can show that du d theta square plus u square is actually is equal to 2 E minus V by m h square. So, if you now take this thing a little bit, so this is, I would say, this is general definition for an arbitrary central force law. This is general, okay. And if you now compare this thing with this thing, you will actually find that this C is nothing but E by it will be actually, I would say, m h square. Okay. So, that is just to tell you that C, this C is not an arbitrary constant, but you can actually relate this to the total energy and the angular momentum, the mass of the particle. Okay. But here we just again take this C and we continue our calculation. So, that will simply be, so the next line will be du d theta whole square plus u square, okay, plus alpha by u square is equal to C. Okay. Then what I will do, I will again write, again I will do some mathematical trick, I will multiply with this equation, I can multiply 4 u square, and if I multiply it, I will find 4 u square du d theta whole square plus 4 u to the 4 is equal to minus 4 alpha plus 4 c u square. Okay. This you can easily see from this equation. And now I just introduce a new variable. I say let, I use a new color over here, let W is equal to u square, and then your dw d theta will be equal to 2u du d theta. Okay. And then of course, dw d theta whole square will be simply 4u square du d theta whole square. That much I can write. So, this equation finally comes to be dw d theta whole square plus 4 omega square, okay, because u to the 4 is nothing but omega square, okay, is equal to minus 4 alpha plus 4 c omega. Okay. And then I can also write this as dw d theta whole square plus 4 omega square minus 4 c omega. Then I can add 4 c square. I mean, I can add actually c square, simply c square. The objective is clear to the students, I think. We want to make a whole square out of this, and in this side I also add a c square over here. Okay. So, what it gives me? It gives me dw d theta whole square plus 2 omega minus c whole square is equal to c square minus 4 alpha. Okay. Again, you see that we have somehow a very convenient form. Why? Maybe some of you can already see, but some of you cannot. Now, if you simply write this thing as dw d theta whole square plus, I take 4 common, omega minus c by 2 whole square is equal to c square minus 4 alpha. Then I write dz d theta whole square plus 4z square is equal to c square minus 4 alpha, where a new variable again is introduced, z is equal to omega minus or w minus c by 2. You can call this omega or w, whatever you want, does not matter here really. So, this is a form which is of quite importance, because once you have this, you can immediately differentiate that with respect to theta, and you get immediately d2z d theta 2 plus 4z is equal to 0. Okay. So, if you simply do this thing, you will have this. Okay. Of course, you know that to be very puristic, if you do d d theta of this, so there will be actually there will be this thing times dz d theta. But dz d theta, for instance, I am just assuming dz d theta to be not equal to 0, and why you have to think, and you can tell me later. We get d2z d theta 2 plus 4z is equal to 0, because this c square minus 4 alpha is just a constant. So, finally, I get an equation which you all know. This is an equation of a simple harmonic oscillations, but this is for z. So, for z I can actually write the solution will be some b cos I would say, since this is 4, so it is omega square. So, I have to write cos 2 theta minus some theta 0, okay, actually where b is equal to So, c square minus 4 alpha is equal to 4 b square. So, 4 b square will be c square minus 4 alpha. Okay. So, if you have this relation, then actually you will easily see that if you, why this should be b, if you now just take this solution for b, the trial solution for b here, and you just put over here and here, you will actually have this is equal to 4 b square, and from that you actually can have this typical form which is z is equal to b cos 2 theta minus theta 0. Okay. Now, you can say that this theta 0 I can choose to be 0, and then your z will be equal to b cos 2 theta. Okay. So, you see the thing is that now b you know in terms of c square and alpha, c you know in terms of energy, angular momentum and the mass, alpha you know because you know the nature of the force law. Okay. So, actually b you know. Okay. So, z is equal to b cos 2 theta, simply now tell me that omega or w minus c by 2, which was the definition for z, this one is equal to b cos 2 theta, and then I can write this omega is equal to c by 2 plus b cos 2 theta. Now, what is omega or what is w, whatever you want. So, this is by definition is u square or 1 by r square. So, 1 by r square is equal to c by 2, I can call that a, c by 2 I can call a plus b cos 2 theta. So, you see, can you now see the polar equation of the orbit under a harmonic potential, but can you intuit the nature of the trajectory? For that, what we have to do, we have to write 1 is equal to a r square plus b r square cos 2 theta. Okay. Now, r square we all know this is x square plus y square. So, x square plus y square times a plus b. Now, r square cos square 2 theta is nothing but this is equal to r square cos square theta minus r square sin square theta, that means x square minus y square. So, x square minus y square, that is equal to 1. So, from that I will have actually something very interesting. I can have x square a plus b plus y square a minus b is equal to 1. Now, you can have some idea of the trajectory, because if you simply write this equation with a new color over here, you can simply say that x square by 1 by a plus b, okay, which I can also write root a plus b whole square plus y square by 1 by a minus b root and the whole square of this is equal to 1. And you can say, since a is equal to c by 2 and b is equal to half root over c square minus 4 alpha and alpha is greater than 0, then actually you can have a greater than b. So, a not equal to b, and that is why you will have this thing and this thing unequal, and you have the trajectory as an ellipse. Okay. So, you see here also strangely we are all obtaining a conic section which is an ellipse with its semi major axis to be equal to 1 over root a minus b, okay, because a minus b is somehow less than 1 plus b. So, semi major, so 1 by A minus B will be greater than 1 by 1 plus B. So, that will be, and so will be their square roots. So, this will be actually the semi major axis and this will be the semi minor axis. Okay. So, you see that here for we have seen that just like the inverse square law of force, although several nature of motion, the analysis, the V effective, the radius of the circular orbit, they are quite different from that of the inverse square law, but at the end of the day, even for this harmonic potential, that closed trajectories are also ellipse. Okay. So, with that I am just wrapping up this lecture. Thank you.